First of all, I would like to thank the organizers for inviting me, and in particular, Mats, for taking care of all the logistics in terms of getting me here. So thank you, Mats. So my work is, I'll show you, we're sort of working more in the chemical sensing and characterization of materials for these purposes. So before I go anywhere, I'm required to put the disclaimer up. So anything, that in any way, shape, or form identifies a commercially available product or vendor or anything like that, it is not meant to be an endorsement, but merely to help you sort of figure out how we did things. I'm required to say this. All right, so I'm from NIST. That, if you're not familiar, is the premier national standards organization in the United States. So one of our main, raison d'etre is to help the U.S. economy grow and help the commerce. We are part of Department of Commerce, after all. So as you can imagine, there's a huge interest, and there's a very large program at NIST devoted to additive manufacturing and pushing it forward. So if you're interested, you can go to this website or just ask me. I can put you in touch with the relevant people who are working in additive manufacturing. Very broadly generalizing here, the engineering lab is working on things like the material characterization and process control and how to improve the final quality of the product. The materials characterization lab, which is mostly chemists, are sort of working on the relationship, amongst other things, of how the starting materials quality affects the final product's quality. And then you have the physical measurement lab, which is mostly physicist. So I'm a chemist who works in the physics lab. There, the focus is mostly focused on developing new measurement science tools. So the idea here is, for instance, to be able to measure temperature by looking at the emissive properties of materials. So you can have a better process control. So again, this is sort of a holistic program that looks at the entire process and how we can improve it to push additive manufacturing forward. So at NIST, I'm part of what's called the thermodynamic metrology group. That's a group that is, and this is a mouthful, charged with the realization, dissemination, and maintenance of the national standards for temperature, pressure, humidity, vacuum, and helium leaks. So we sort of provide the basic calibration services, but we also do a lot of innovative research. And over the last few years, a lot of our focus has been in photonic sensing. So one of our projects that's led by Jay Hendricks has been on the photonic pressure standards. So rather than using mercury manometers, using refractive index of gas to define pressure. My team does mostly silicon photonic sensors, so a lot of work in temperature, but also in humidity and increasingly in pressure. So you might ask, what are people who do photonic research doing in additive manufacturing? Well, we're mostly approaching this from a perspective of the users. We want to do what almost every user in playing around with 3D printing is doing, which is to conserve their resources, time and money. And we want to take advantage of the freedom of design that comes from additive manufacturing. Well, sometimes comes. So there are two areas that we are sort of interested in. One is instrumentation. Can we shrink it down, make ours more deployable, more easy to use, almost, it's a very crude way of putting it, but idiot-proof in a way. And the other is this idea of being able to do chemically active materials. So make little blocks that you can store gases, release gases on demand, and are safer to handle, and also being able to print sensors that can sort of pick up gases and can give us information about what gases are present. So these would be things like you could do in the terahertz or microwave. So again, building chemical sensors, things like that. So let's talk about metals first. So our interest in metals came because we have a team. This is Jim Fetchek, Julia, and Steve Eccles working on this. And the idea here is to make a new national standard for vacuum. So more specifically in the XHV. So this is 10 to the minus 10 pascals or lower in pressure. So the idea is to look at the loss rate from an atom trap. So if you can calculate the original cross sections of the atoms in the atom trap really, really well, and that's going to be the big push there in that particular project, then you should be able to look at the loss rate and relate that to the residual gas pressure present in the chamber. So that's how we wanted to be able to define ultra high, extremely high vacuum. So this is the apparatus as it exists. This is a MOT. So you can see it's a very large thing. There's a lot of connectors, things like that. And one of the questions that we have is, can we sort of, rather than doing free space optics, bring waveguides directly into the chamber, eliminate all of these feed-throughs and other connectors we have where things can leak, and really create a more compact, robust system that can be suitable for these sort of operations. We've been playing around with embedding fiber optics in 3D printed materials, so we've mostly worked with plastic materials, sort of expose these to radiations, things like that. So kind of some fun experiments there. So, but before we can do things with metals, the question we always had was the same one you guys had in the UK, which was, so you're creating these 3D printed materials, they're lighter, the density is lower, so there are all these voids. Are these suitable for XHV applications? So the basic measurements we've done are the same ones everyone in vacuum does, the rate of rise, the throughput, and accumulation type measurements. And we can go over these if you were interested. Again, the measurement protocol is the standard one people have been doing in vacuum science for a long time. And really you can also say it's very laborious. It's time consuming. Basically, you're trying to get rid of all the water and hydrogen gas that's in your sample holders. So once you do that, then you can look at what's coming off of your parts. So we started with titanium, and these came from Walter Reed National Medical Center. And so we started with titanium sheets because it lets us create a very large surface area compared to that of the sample. So here's an SEM, and this is really what concerned us right from the beginning. You see the SEM, you see all the voids, you see the density drop. So we were worried about water molecules. Are there waters that are trapped somewhere, so they're going to have a long outgassing rate, and that's going to destroy your vacuum over time? Because we want to get to a very low level and then stay there while we do experiments and have our instrumentation work for a long time period. So let's look at some of the data. When you look at the rate of rise, the first thing you notice is the sample chamber is pretty much on par with the titanium sheets, even though the surface area is so much larger. That's in a way, it's a good news, but from an engineering perspective, the number you care about is the flux, and you can see the flux for the titanium part is significantly lower than stainless steel, which is the good news here, right? This is what you expect to see. What's coming most off of it is mostly just hydrogen gas. So again, these are all good news. So that seems to say, all right, we should be fine for using these for these purposes. So we then went ahead and just had a very simple chambers printed. So these are test chambers, there's hollow cylinders, and these tubes here are welded on, and they are meant for a spinning rotor gauge experiment. So you can measure the outgassing rate and how much the pressure is building up as these chambers sit there. So far, what we can say is that the pumped on curves, just like as you found, look very similar for both titanium and the 3D printed stainless steel. And in fact, they're very similar to what's in the literature for normal stainless steel. So what that tells us, the water molecules that are coming off of these, they are just sort of interacting with each other, or just with a bare surface. Their activation energies don't seem to be very different from what you have typically seen in materials. Right now, we have experiments going on looking at the activation energies of water. So we're doing the same pumped on curves at different temperatures to be able to extract those. So that work is still underway. With stainless steel, we have some more data on hydrogen outgassing, but we're not quite ready to talk about it. We're still analyzing it. And one of the things we're looking at is when you get stainless steel parts made from different vendors, different processes, different starting materials, you get very different microstructures, right? So one of the questions we have is, given the different amounts of additives people are adding, how is that changing the hydrogen outgassing rate? So that's sort of work that we're working on right now, and hopefully we'll have results relatively soon, just in a couple of months. So let's shift to some of the chemistry work. So this is work that's going on with our collaborator, Matt Hottings at American University in Washington, D.C. The idea is very simple. It is, can you take the basic feedstock material like ABS, which is chemically inert, because, well, that's useful for most cases, and make it more specifically attracted towards certain chemicals? So one of the ideas we had was, A, can we store different gases in here that we can release for our chemical sensing processes when we want them? So essentially on-demand release of chemicals. And also, can we build sensors? So with 3D printing, this is people have done this with polyethylene in the terahertz for a long time. You can print waveguides, you can print whispering mode resonators, bandpass filters, things like that. So our idea again here is, if you could make a material that can absorb different gases like hydrogen or volatile organic compounds, things like that, then its dielectric constant should change as it picks these gases up. So if you could build sensors in the terahertz, then you would have a 3D printed chemical sensor, things like that, that you could build into your apparatus. So if you had a material that could store, let's say, hydrogen gas, then you could use terahertz to actually just measure how much gas you were loading in real time. So there are applications like that we are exploring. So our process is very simple. You take, or at least in theory it was very simple. So you start with ABS or PLA. You mix in nanoparticles, you blend them, and you extrude a filament that you can then use for printing. Of course, you're not trying to find a material that actually will print, or the materials that won't degrade. So first thing we did was we were at least smart enough to start with a more robust system. So we started with TiO2 nanoparticles, mostly because they're harder to destroy. So one of the first things we did was we just made different blends. So starting with pure ABS, can we print? Yes, we are competent in that. Sure of our competency there, we went up to 1%, 5%, 10%. After that, it just basically becomes too brittle and doesn't print. So what do you find? Well, when you look at the X-ray diffraction spectra, in fact, when you print the piece, titanium is throughout the entire piece. So that's good news. It's not sort of clustering out in one giant chunk somewhere. Its presence definitely changes the optical properties of ABS. So its native fluorescence is being quenched. More importantly, the mechanical properties, it sort of strengthens up and then gets weaker at higher loading factors. And that's, when you look at the IR spectra, that's because the TiO2 nanoparticles start to decompose or break down the polymer backbone. So this was a encouraging result. So we moved on to gas storage materials. So the chemicals we chose to work with are called metal organic frameworks, or MOFs. In the gas storage and uptake community, these are very famous molecules, mostly because, well, they have these pore sizes. So they are crystal materials. They have these pore sizes that you can change. You can sort of engineer how big the pore size is by simply changing the organic linker molecules. So you can make these molecules be more selected towards certain gas molecules, things like that. So we started with MOF5, which is very well known for its tremendous capacity to store hydrogen gas. And then I'll tell you why we moved to ZIF5 and edge coast. Because basically, things that can go wrong will always find a way of going wrong. So we started with, it started out all well and nice. You make your composite, so the filament, you see crystals there. You 3D print the piece, the crystals are all nice and present. If you look at the EDX map, those are zinc oxide. So these are real crystals, they have the zinc, so everything looks all fine. It should work. So let's look at the ABS itself, the native ABS. Well, it turns out it mostly likes to store water. In fact, a lot of water. And 360 hours after you bake it out, you can watch the water come on and on. Up to 0.36% by weight is just water. The good news is you can still outgas most of this water out. So it's still good enough for UHV applications, so we can do our measurements. But you need to bake it for 3 days at 100 degrees to get rid of all the water. So when you look at the hydrogen uptake, you can load hydrogen, you can desorb it reversibly, go back and forth. If you look at just ABS, the composite compared to that definitely has more hydrogen loading capacity. Now, hydrogen loading capacity was only 33% of what we expected based on theoretical loading capacity of MOF. And the reason, unfortunately for us, it turns out, was because somewhere between the synthesis and purification and the blending process, our MOF samples were exposed to humidity and they decomposed. So the values here are they match up with what people have seen in literature for decomposed or degraded MOF5. So while this was a positive in the sense of, yes, the idea works, you can process all these materials and change the basic properties of MOF, it was a little disappointing to be like, it didn't quite work the way we wanted. So that's why we switched over to edge coast and to ZIF8, because they are more robust against humidity. So when you make these samples, you blend them, you can see the edge coast is fine here, you blend it in with ABS, you can extrude it, print it, and then it sits there for 28 days. Nothing bad happens to it. In fact, you can take it, dip it in water, leave it in, come back, and nothing has happened. Water hasn't diffused through and decomposed your crystals. So that's good news. So we have also done this, SEM, DSC, IR characterization, so it's all fine. So what we have done up to now is we've been measuring the nitrogen uptake for these, and you can see here, for different blends, between ZIF8 and MOF, edge coast, you can see the different porosities different surface areas for different plastics. You can also see that the kinetics for loading the different gases are different. So again, you're not just simply changing, something in the polymer. This is an actual property of the material you've added to the ABS. So that's been one of the main questions. Are you simply changing something in the structure of the polymer that's changing these properties? So what our results are indicating up to this point is, no, this is an actual, the crystals are actually functioning like the way you expect them to function. The hydrogen work is going on right now, so hopefully we'll have those results, but most of these have already been posted on the archives. So if you're interested, you can just download them from there. So I'll just summarize here. One of our results so far is, again, just like others have found, that titanium and stainless steel, they're generally speaking compatible with vacuum operations. One of the things that we have found is titanium was fantastic for vacuum operations. We had no problems getting chambers printed. But we had some issues with the stainless steel. Our record was about 33% success rate in not getting helium leaks. And typically what was happening was, first time there were just holes, you could see them. Second time around, the part came in, and once we cleaned it, so for us, the one issue is if people touch with bare hands, that leaves behind oil that outgasses. So you have to do scrubbing. Once we scrubbed it, there were helium leaks. So things like that, that's one thing I would say if you're worried about doing vacuum operations, you need to be mindful of. Titanium, for whatever the reason, works perfectly. In terms of these chemical selective materials, so far our work has indicated that this is a viable route. You can make materials to store gases and make sensors out of it. So I would like to thank the students who actually did most of the work. These are math students and our collaborators, Peter Leacros from the Walter Reed Center, who did the titanium sheets printing, and Nathan Castro, who's helping us with the biomedical engineering aspect of things. So hopefully we'll have those results too soon. And with that, I'd like to thank all of you for your kind attention.
Thank you so much. Thank you so much.
No
impressive. How much are you cooperating with an industry in these fields?
So we usually just get our stuff from industry whenever we can. So we just sort of get people to send over some money, and they'll print it for us.
Okay, okay. And what's the driving force within industry or within the development within industry for your field?
So for our field, the way this whole thing started was we were having conversations with a couple of defense organizations, contractors, and as we sort of got interested in, for their applications, they're seeing a lot of failures. So we were interested in how much air is present and what are the different chemicals present that are so one of the theories was parts are failing at high temperatures or under repetitive motions is because there are pockets of air present. So this is how in the metal we sort of start thinking about it. And then in terms of being able to think about the atom trapping, that I think is sort of us thinking.
Okay.
But it sort of, when you talk to the larger community, there is definitely interest in being able to quantify things and use them in these sort of environments.
Have you a number of commercial applications already that are using your theories, or how far have you come, or is it a secret, or how much can you reveal?
So mostly this is an academic interest.
Yeah, yeah.
So from an academic point of view, there's a lot of interest. TiO2 paper we had, for some reason, it ended up attracting a lot of attention in Asian countries because TiO2 can self-clean under UV illumination, breaks down pollutants. I mean, that's just Lego blocks. I never cared as a child whether they were dirty or not, but apparently it matters a lot. So there's a lot of interest from those perspectives, being able to clean things. In informal conversations we have had, there are a lot of interest in being able to 3D print, for instance, gas masks that can break down nerve gas agents, things like that. So being able to functionalize these plastics, so you can print them, so you can do chemical reactions or things like that, or storage or degradation of products is of interest. But a lot of it is in early research phases. So you're starting to see it come out in literature now.
Interesting. Thank you so much. Big hand.